Hey folks, and welcome to our next lesson. We have everyone's favorite topic in geometry today, proofs. Now, you're probably screaming into your microphone right now wishing that I could hear you. However, there's actually something good. The reason old school proofs were really complicated is because it was rather difficult to show that things were right angles, things had parallel lines, that distances were the same. We didn't have the tools for it. But this entire unit has been the link between right angles, parallel lines, and same distances, and algebra. So we're actually going to see today that using the Cartesian plane, our proofs are a lot easier. What we won't be doing today, we don't need a two-column proof. You don't need to write the given in the proof. You don't need to do any of that. And you're actually going to see that this is a lot easier, and it's a reason why, after about 2,000 years, the Cartesian plane is really helpful. Let's take a look at our first example. So our aim is, how does the Cartesian plane make proofs much easier? And I promise, much easier. This is our first example. Pause the video and write it in. Now, they're always going to say that the use of a graph is optional, and yeah, you can do this without a graph. Yeah, we're not going to do that. We're going to use a graph. So step one, graph it out. So I know my points are bigger, so I just made my scale a bit larger too. Okay, I'm going to graph them out now. All right, so we have our graph. Yay! We want to prove that it's an isosceles triangle, and remember, with isosceles triangles, we have two sides are congruent, and we're going to say that one side is not congruent. We're using the inclusive definition. We just want to make sure that we're showing all three sides. So all we're going to need to do is find the distance of this segment AC, this segment AB, this segment CB. Two are going to be the same, one's going to be different, and we can do that in two ways, either distance formula or Pythagorean theorem. I'm going to do it using Pythagorean theorem here just because, well, I want to. Let's see. So AC, this is going up 6, this is going over 6. So this is going to be 6 squared plus 6 squared, that's 36 plus 36. So this is going to be the square root of 72. This is going over 6, this is going over 6, so this is 6 and 6, so that's also going to be square root of 72. Distance of this is actually really easy to find because you just count it. I mean, it's 10 and 12. Cool. So that means that two sides are congruent, one side isn't. This is an isosceles triangle. We're done. So that proof was done really quick, and it was using the tools that we know how to use. Because we were just asked for an isosceles triangle, and that just relies on the distances between the points, the sides, we just use distance formula. Let's talk about a trapezoid right now. Trapezoids need two sides to be parallel, and that's it. They just need two sides to be parallel. So we can show parallel by just same slope. Now, it's also important to recognize that two sides need to be parallel, the other sides can't be parallel. Because if they were parallel, we would have a rhombus or a rectangle or a square, and we're just trying to show a trapezoid. So let's take a look at how we do this with slopes. So let's take a look at our next example. Pause and write it in. Cool, we want to prove it's a trapezoid. Trapezoids just have two parallel sides and two non-parallel sides, so we're going to deal with slope. Let's graph it out. Okay, so we're probably already thinking that AB is going to be parallel to DC, and that AD and BC are not going to be parallel. They look like it. You cannot just put it looks like it, so that's my answer. I wish it could, right? We're just going to find the slope of it, and we're just going to do it with rise over run. That's it. I'm just going to count boxes. Now, I realize I don't have boxes on my paper. However, I'm going to do exactly what I did up here in this example and just draw them out. Okay, so I found my slopes. This is a fourth, this is 2/8, this is 3/1, this is -2/3. If you're wondering why this one is negative, it's because this has a negative slope. It has to decrease. You might be saying, oh no, none of them are the same. Yeah, they are. These are the same because I can simplify that fraction to 1/4. So I can say AB is parallel to DC, same slope. B is not parallel to BC, different slopes. ABCD is a trapezoid. We're done. So we've seen two of the tools we're going to use. Distance formula / Pythagorean theorem is our first one. Parallel lines is our second. Lastly, it's going to be perpendicular lines. Now, we know from this unit that perpendicular lines have a negative reciprocal slope. So if one line had a slope of 3/2 and another had a slope of -2/3, the two lines meet at a right angle. It could be a right angle like this, it could be like this, it could be anything so long as they meet at a right angle. We're going to prove something is a square. Well, to prove it's a square, all four sides have to be the same length, and all four angles have to be a right angle. Let's take a look. So this is our last example. I already graphed it out. You may want to pause the video and just draw it in. Now we want to show it's a square. We know that squares have all sides are congruent, they're all the same length. And we also know that squares have all right angles. In order to show that all sides are the same length, I'm just going to do the Pythagorean theorem, and that's actually going to also help us with all right angles. So let's show it out. Okay, every triangle that I've just drawn here in blue has one side that's 1 and a second side that's 4. Well, all the sides are just going to be 1 squared plus 4 squared equals c squared. That's 1 plus 16 equals c squared. That's 17 equals c squared, so that's 17 square root equals c. We just showed it. All the sides are the square root of 17. So I can say that ER is equal to RQ is equal to QS is equal to ES is equal to the square root of 17. We proved all the sides are the same. We're a minute and a half into this video. Now, in order to prove that all the right angles are the same, all we need to do is show that this slope is at a right angle to this slope. Here's how we can do it. This slope is 1/4, so the slope of ER, I'm using m because slope is m, is equal to a rise of 1, a run of 4. The slope of SQ is the same thing. The cat's trying to be let into the room. That's the scratching you hear. This slope is negative. It drops 4. It's over 1. It's the same slope as ES. These two slopes are negative reciprocals. So that means that ER is perpendicular to RQ. We've proved it's a square, we're done. So if at this point you're screaming saying, why was it that easy and why weren't proofs that easy before, it's important to recognize the history of it. The Cartesian plane, otherwise known as the XY plane, has only been around for about 600 years. It wasn't around before then, we didn't have it. The ancient peoples who made proofs, notably the Greek and the Egyptians who they learned from, just didn't have the tool. That's why connecting algebra and geometry is such a powerful thing. Now, we're really only going to use 3 tools with this. We're going to use parallel lines, we're going to use perpendicular lines, we're going to use the distance formula. Those 3 are how we're going to show everything. And I've attached a resource that you can look at. It just lists out, like, if you're proving this is a square, here's what you do. If you're proving this is a rectangle, here's what you do. If you're proving this is a trapezoid, here's what you do. So, Delta Math doesn't have anything for this, unfortunately. So there is a classwork attached. You're going to choose 2 out of the 4 problems. There is no extra credit for doing extra ones, so please just choose 2. And you're just going to show your work as best you can. You can take a picture of your work in your notebook. You can try to do it on the computer using the equation editor in Google Doc. It is your call. If you have any questions, you know where to find me, folks. Have a good one.